We will now be applying sampling plan concepts to life and reliability testing. When we use the binomial distribution, the sample size and AQL being given, we can arrive at the acceptance norm in terms of maximum number of defects allowed in the sample. Or, given N and C, we can work out the threshold % defects in the lot that will get cleared by the sampling plan at, say, 95% confidence level. On the other hand, using the Weibull distribution, we can work out the probability of failure, given instantaneous failure rate and the corresponding testing time. We will now bridge the two using a simple example. We are given a sampling plan where N equals 115, C equals 3. This happens to be acceptance criteria for a lot for which we need to find the failure rate. Beta and testing time are given. Using binomial distribution, for probability of acceptance 95%, we can work out the maximum defects % in the lot. It is this % defects that must not be exceeded at the testing time given, and we use that to back-calculate the failure rate using the Weibull distribution. The % defects is calculated using the cumulative binomial distribution function and is found to be 1.2%. For the Weibull distribution cumulative function, the first term is the product of testing time and the instantaneous failure rate that we are looking to determine. Alpha is taken as 1. Beta is given as 2. Equating this to 1.2% gives a value of t multiplied by lambda t. Since testing time is known, failure rate, lambda t, can be determined. This can be extended to rejection sampling. Say a lot with failure rate 5x, the lot accepted is to be rejected. What is the % defects in the lot? Since we have already determined the acceptable failure rate, the failure rate at which the lot is to be rejected can be calculated. This time we know the value of the first term of the Weibull cumulative function since both testing time and the corresponding failure rate is known. This gives a value of 5.86%, which now becomes the rejectable hazard rate. Okay, let us try out a couple of problems. Let us consider a material where the failure rate drops with time. Beta equals 2/3. The rejectable hazard rate is 0.00005 per hour at 1,000 hours, which is also the testing time. If sample size is 200, what is the value of C which will ensure that the probability of acceptance of this lot is less than 10%? The second problem refers to the earlier instance when N equals 115 and C equals 3. Calculate the customer risk of using the plan if a lot is per RHR of 5.86% defects is received. For the first problem, we have the testing time, failure rate, as well as the beta value for the distribution. So we can calculate the % probability of failure, which is 7.19%. Using P equals 7.19%, given N equals 200, probability of acceptance as 10%, C can be determined. For the second problem, we check the probability of acceptance of a lot with 5.86% defects, given that the sampling plan has an acceptance criteria of C equals 3 for N equals 115. Since N, C, and P% are given, the probability of acceptance can be calculated directly as 8.97%. This represents the customer risk for the sampling plan, and since it is lower than 10%, it is acceptable. This completes the basics of reliability and life cycle testing. In future videos, we will discuss reliability of systems, MTBF, and lots more.